Okay, hello to all of you. Let's discuss chapter number 2. Chapter number 2 is basically a chemistry chapter, and in this chapter, we are going to talk about some of the chemistry, and chemistry is very much related to biology. So, to go into the deep in biology, you first of all need to have a review over chemistry because basically, living organisms, biology is the study of life, and living organisms, they are basically made of cells, and cells, they are made of biomolecules, and these biomolecules, they are basically made of some elements, and these elements are bonded with each other. So that's why to understand life, it's very important to have a review of the chemistry, because it's very important to understand chemistry and relate and we need to relate how chemistry is involved in the biological system. Okay, so first of all, few terms. Organisms are composed of matter. So what is matter? Matter is anything that takes space and has mass. Now, matter is made of elements. Now, what is an element? Element is a substance that cannot be broken down to other substances by chemical reaction. And these elements, the different kinds of elements, we are going to go over the periodic table also. And these elements, they are made of atoms, and these atoms, they are made of further subatomic particles. We will talk about all those subatomic particles, and these elements, they combine in a specific ratio and they form compounds. So what's a compound? A compound is a substance consisting of two or more elements in a fixed ratio, and a compound has characteristics different from the elements of which that compound is made. For example, sodium chloride. Now, sodium chloride is a common salt. It's a table salt. So sodium chloride is made of sodium, which is an element, which is a metal, and it is made of another element called chlorine, and chlorine is a gas. So sodium, which is a metal, chlorine, which is a gas, so when they combine and they form a compound called sodium chloride, and sodium chloride is a salt. So the compound which is made of these elements, it has the characteristics different from the elements. Like sodium is a metal, chlorine is a gas, and sodium chloride is a salt. About 20 to 25% of 92 natural elements are required for life. So out of 92 natural elements, so there are some artificial elements also which are made in the labs. So 92 out of 92 natural elements, 20 to 25% are required for life. So they are the essential elements. They are the essential elements for life. So carbon, hydrogen, oxygen, and nitrogen, they make up 96% of the living matter. And there are some other elements which are also involved in life forms. They include calcium, phosphorus, potassium, and sulfur. And there are some trace elements which are required by organisms in very small quantities, like for example iodine. So this is a table which shows the elements which are there in the human body. So carbon, oxygen, hydrogen, and nitrogen, they are like around 96%. So these four compounds, they make 96% of the human body, and these are the other elements. Now, as I said, every element is made of atoms, and atom is the smallest unit of matter, and these atoms, they have subatomic particles like neutrons, protons, and electrons. So electrons, they have negative charge, protons, they have positive charge, and neutrons, they have no charge. So basically these neutrons and protons, they make the core of the atom. So they are present in the nucleus, in the atomic nucleus, and electrons, they are negatively charged, and they keep on moving in energy shells around this nucleus. And the unit of the mass, so basically neutrons and protons, they are present, and protons, they are present in the nucleus, and they make the mass of the atom. And the electrons, which are negatively charged, and these electrons, they are very, very light in weight. They do not contribute much to the weight of the atom. So the basic mass of the atom is because of the mass of neutrons and the protons. and it is measured in unit called Daltons. So this is the way you can see. This is the nucleus, and in the nucleus there are protons. There are protons and these are neutrons. And around the nucleus, these are the energy shells in which these electrons, they keep on moving. So there are two terms which we need to know. What is atomic number and what is mass number? Atomic number is the number of atomic number is the number of protons an atom has. Okay, atomic number is the number of protons an atom has, and for a neutral atom, number of protons and number of electrons are always same. So which means that if you know the atomic number of a atom, you know how many protons are there. If you know how many protons are there, you know how many electrons are there. So atomic number is equal to atomic mass. Atomic number is equal to number of protons and also equal to number of electrons. And mass number is the number of neutrons and protons in the nucleus. Okay, now we need to know what are isotopes. Now isotopes are the different atoms of the same element which differ by the number of neutrons. Okay, so they have the same number of protons and electrons, but they have different number of neutrons. So that is what are the isotopes. The atoms of an element that have the same number of protons but differ in number of neutrons, they are called isotopes. For example, like carbon has three different kinds of atoms: carbon 12, carbon 13, carbon 14. Okay, so carbon 12, carbon 13, carbon 14. So all these three atoms of carbon, they have same atomic number, which is 6. Okay, so which means that they have same number of electrons, same number of protons, but what is the difference? The difference is the number of neutrons. There are many examples of isotopes. Like hydrogen also exists in 3 forms: hydrogen with atomic mass number 1, hydrogen with atomic mass number 2, which is called deuterium, and then hydrogen with atomic number 3, that's called tritium. So hydrogen also exists in different forms, and they're called the isotopes. So isotopes are the different atoms of the same element. Some of the isotopes are radioactive. Some of the isotopes are radioactive. So they decay spontaneously, giving off particles and energy. And these radioactive isotopes, they can be used as tracers. They can be used to detect cancer in the body, because for doing this kind of a thing, basically in the hospitals, in the cancer centers, basically when somebody has a cancer, these radioactive tracers can be used for the diagnosis of cancer. So basically, like as I said, carbon also exists in different forms. So the radioactive carbon is present in it is basically like in the glucose. So glucose is a sugar. So glucose has carbons in them. So the glucose with the radioactive carbon is given to the patient. So the patient drinks it, and wherever there is a cancer in the body, at that place, the cancer cells, they divide very fast. So cancer cells, they have an abnormal cell division. So wherever in the body the cancer is there, at that place, when the patient drinks the radioactive drink, that radioactive drink which has glucose in it, it's going to be going and getting more in the area where the cancer is. So, and then where the cancer is, this glucose will be going there more, because those cells need more energy. So that will be deposited there, and because it's a radioactive carbon, it's going to decay, it's going to give radiation, and it can be used for diagnosis. So you can see here, this patient has taken radioactive glucose and it is showing up here. This is in the form of the radiation. Also, these radioactive tracers can also be used for radiometric dating. So basically, because these radioactive elements, they have a half-life. So in a specific amount of time, in a specific amount of time, in the specific amount of time, they these radioactive material, they decay. On the basis of that, the age of rocks and the age of skeletons and all these things can be figured out. So this procedure is called radiometric dating. Okay, so now let's talk about coming back to the atom. So as we know that the core of the atom is made of the core of the atom is the nucleus. In the nucleus there are protons and neutrons, and around the nucleus are different energy shells, and in these energy shells are electrons which are moving. So on the basis of, so these are like, this is the atomic nucleus. These are the different energy shells, first, second and third. So these electrons, they're moving in these energy shells, and on the basis of in which energy shell these electrons are, these electrons, they have the energy. Okay, and that energy is called the potential energy. So first of all, what is energy? Energy is the capacity to cause some change. What is the potential energy? It is the energy which is because of the location or structure. So potential energy is the energy that matter has because of its location or structure. And the electrons, they differ in the potential energy, and their potential energy is on the basis of in which energy shell they are. So if this is the nucleus, these are the different energy shells. So if the atom is in the third energy shell, it will have more energy as compared to if it is in the second shell or it is in the first shell, because energy is required because these electrons, they're negatively charged, and the nucleus is positively charged because of the presence of protons. So this positively charged nucleus is going to attract these electrons towards itself, is going to attract the electrons towards itself. So the more the electron is away from the nucleus, it has more energy, which means more energy was spent to make this electron move away from the nucleus, because nucleus is pulling electrons towards itself. So you can see that if the electron has to move from here to here, some energy is required, and if the electron has to move from here to here, energy is required, energy is absorbed. And when these electrons fall back from this energy level to this, or from this to this, they lose energy, they release energy. And the chemical behavior of an atom is determined by the distribution of electrons in the electron shells. And this is the periodic table, which basically organizes the different elements. So these elements, they are distributed on the basis of they're basically these elements in a periodic table, they are organized in different rows and different columns. So the rows are called periods. Like this is the first period, and the first period has hydrogen and helium. Second period has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. And third has sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. So this is the third period. And these columns, these vertical columns are the families or the groups. So this is the first group, this is the second group, this is the third group, fourth group, fifth, sixth, seventh and eighth. So basically you can see a trend in the periods and the families. So in a period, this is the first period. In this first period, there's a hydrogen and there's a helium. Okay, so hydrogen has 1 electron, helium has 2 electrons. So so these electrons, they are distributed in the energy shells on the basis of some rules. Let me go back here. Or we can, yeah. So this is the first energy shell, this is second energy shell, and this is the third energy shell. So in the first energy shell, only 2 electrons can be accommodated, and this is the second energy shell. In this, 8 electrons can be accommodated, and this is the third energy shell. In this also 8 electrons can be accommodated. So 2 here, 8 here, and 8 here. Okay, so the first energy shell can accommodate 2 electrons, second energy shell can accommodate 8 electrons, and the third energy shell can also accommodate 8 electrons. Okay, so this is the way how electrons are distributed. So if an atom has, like sodium has 11 electrons, so 2 electrons will go in this shell, 8 will go in this shell, the last one, 11th, will be going in the third energy shell. Okay, for carbon, like 6 electrons, so they're going to be going 2 here, 4 here, 2 and 4. Okay, another important thing is, like the first energy shell can have maximum of 2 electrons, second energy shell can have maximum of 8 electrons, and third can also have maximum of 8 electrons. So if these energy shells are not completely filled, then the atoms, they are unstable. Okay, if these electrons in their outermost shell, and the outermost shell is also called a valence shell, and the electrons which are present in the valence shell, they're called valence electrons. Okay, so if the valence shell of an atom is completely filled, then that atom is inert, or that atom is unreactive. But if the valence shell is incompletely filled, then that atom is unstable, or that atom is reactive, and this is called octet rule. According to the octet rule, the outermost shell, which is called the valence shell of an atom, should be completely filled. If it is not completely filled, then that atom is reactive, because that atom is unstable. But if the outermost shell is completely filled, then that atom is inert element or unreactive. So now let me show you some of the examples from here what I explained. Now this is the first element called hydrogen. Hydrogen has 1 electron. So its 1 electron is going to be going in the first energy shell. Now this is helium. It has 2 electrons. So the 2 electrons are going to be going in the first energy shell, right? But if you look at the example of hydrogen and helium, in hydrogen there is only 1 electron which is going to the first energy shell. Helium has 2 electrons which are going in the first energy shell. So the outermost, so the first energy shell, the first energy shell is the valence shell for helium, and it is completely filled. So helium is inert element, it's stable. On the other hand, hydrogen, its valence shell is the first energy shell, and it has only 1 electron. So it means that its valence shell is not completely filled. So this atom is not stable. So hydrogen is reactive. So this is the first period. In the first period, you can see hydrogen has 1 electron, so it's going in the first energy shell. Helium has 2 electrons, they are also going in the second energy shell. So in a period, the same energy shell is being filled as we go from left to right. In the second energy shell, in the second period, going from left to right, you can see this is lithium, this is beryllium, this is boron, this is carbon, nitrogen, oxygen, fluorine, and neon. In lithium, there are 3 electrons. So 2 go in the first energy shell, the third one go in the second energy shell. This is beryllium, 4 electrons. 2 go in the first energy shell, and then another 2 go in the second energy shell. This is boron, 5 electrons. 2 go in the first one, 3 go in the second one. Nitrogen, same thing, nitrogen. So what is happening as we move in a period from left to right? In the second period, the second energy shell is being filled. So here it's 1 electron, here are 2 electrons, 3 electrons, 4 electrons. So as we move from left to right, the second energy shell is being filled. And as we move from lithium to neon, neon has 10 electrons. So 2 go in the first energy shell, and in the second energy shell, how many electrons go? 8. So this neon, in the neon, the second energy shell is completely filled. So neon is also inert element. And same thing in the third shell, you can see as we are moving from sodium going up to argon, the electrons are being filled in the third energy shell. Sodium has 11 electrons. So 2, 8 and 1. 2, 8 and 1. So 2 go in the first one, 8 go in the second one, and the 11th one goes in the third energy shell. Magnesium, 12 electrons. 2, 8 and 2. 2, 8 and 2. So 2 go in the first one, 8 go in the second one, and another 2 go in the third one. Aluminium, 2, 8 and 3. 2 go in the first one, 8 go in the second one, and 3 go in the third one. Silicon, 2, 8 and 4. 14. Phosphorus, 15. 2, 8 and 5. So basically what is happening here is, in the third period, the electrons are being filled in the third energy shell as we are moving from left to right. And as we reach to the end, when we reach to argon, which has 18 electrons, 2, 8 and 8. So the last energy shell is completely filled. The valence shell is completely filled, and that is why argon is also an inert element. So basically this is the way periods, this is a pattern of periods in the periodic table. So this is the first period, this is the second period, this is the third period. In the first period, the first energy shell is being filled. In the second period, the second energy shell is being filled. In the third period, third energy shell is being filled as we move from left to right. But also in the periodic table, there are columns, and they're also called groups or families. So if you look, this is the first group. Oops. In the first group, you can see this is hydrogen, this is lithium, and this is sodium. So what common thing you see in this? The common thing you see here is hydrogen. In the hydrogen, the first energy shell is being filled. In lithium, second energy shell is being filled. In sodium, third energy shell is being filled. So in the hydrogen, there is 1 electron in the first energy shell. In lithium, there is again 1 electron in the second energy shell. And sodium, there is again 1 electron in the third energy shell. So in a group, what is common is, so in this family, what we see that is all of these elements in this group, they have 1 electron in their outermost shell. And if you look here in the last family, which is helium, neon and argon, helium, neon and argon. Helium has 2 electrons, neon has 10 electrons, and they're distributed as 2 and 8, and argon has 18 electrons, 2, 8 and 8. So what common thing we see here is all these atoms, all these elements, they have completely filled valence shell, and that is why they are called inert elements. And this is the 7th family, which includes your fluorine and chlorine. So in these, if you can see, the valence electrons are 7, which means in fluorine 9 electrons, 2 and 7. So the outermost shell has 7 electrons. Chlorine 17 electrons, 2, 8 and 7. So the outermost shell has 7 electrons. So I have already explained what valence electrons are. They are the electrons which are present in the valence shell. What is the valence shell? The outermost shell. Now, what is the orbital? We need to know what is the orbital. So orbital is basically a 3-dimensional space where electron is found 90% of the time. So energy shells are the energy levels in which these electrons, they're moving. Okay, but orbital is a home of electron. So in the energy shell, these electrons are moving, but in the orbitals is like their home. So where they live most of the time. So each electron shell has a specific number of orbitals. Like the first energy shell has only 1 orbital, and that is so there are there are actually four different kinds of orbitals: S, P, D, and F. But we are going to focus only on S and P. So S word comes from spherical. So this is a spherical kind of a orbital. So the first energy shell has one S orbital. Second energy shell. Now the second energy shell has again one S orbital, and it also has three P orbitals. Okay, Px, Py, and Pz. Now the orbital, the S orbital, which is present in the first shell, it's called 1s, and the S orbital, which is present in the second energy shell, is called 2s, and the three P orbitals, Px, Py, and Pz, they are 2p orbitals, because 2 is for the energy level. So there are three p orbitals, px, py, pz, but they are designated as 2p, 2px, 2py, 2pz, because they belong to the second orbital. And these orbitals, they basically hybridize, and they form the hybrid orbitals. Okay, so basically we just talked about some of the atoms. Okay, I think let's stop here, and I will discuss in the next video.